Hello there, and welcome to Sleep Science, where time gently unfolds like a story told in whispers. Before we begin tonight's gentle expedition, feel free to share what time it is where you're listening. How beautifully fitting that we're about to explore time itself. And here we all are, scattered across the globe, each experiencing this very moment, flowing from past to future, never the other way around. Tonight, we're wandering into one of the universe's most quietly profound mysteries. Why time has a direction? Why does it flow from yesterday to tomorrow and never backward? Why do we remember the past but not the future? Why do eggs break but never unbreak? Why do flowers bloom but never unbloom? It's a question that touches everything from the cosmic birth of the universe to the gentle rhythm of your breathing right now. We'll drift through physics and philosophy, through the dance of atoms and the whisper of memory, following time's arrow wherever it leads us. We hope this journey isn't too fascinating, because while we'd love to keep your mind gently engaged, our real goal is to help you settle into sleep. But if you do happen to stay awake a little longer, at least you'll drift off knowing why the universe insists on moving forward, and why that might be the most beautiful constraint of all. So settle in, let your thoughts begin to slow, and let's take a peaceful wander through time's one-way path. Picture this. You're watching a film of someone dropping a glass. It falls, hits the floor, and shatters into pieces. Nothing unusual there. But now imagine watching that same film in reverse. The fragments leap up from the floor, dance through the air, and reassemble into a perfect glass that flies upward into someone's hand. Your brain immediately knows something is wrong. Not just unlikely, impossible. This simple thought experiment touches on one of physics' most elegant mysteries: time's arrow. Most of the fundamental laws of physics are what scientists call time reversible. The equations that govern gravity, electromagnetism, and even quantum mechanics work just as well backward as forward. If you filmed planets orbiting the sun and played it in reverse, the mathematics would still check out perfectly. Yet here we are, trapped in a universe that flows stubbornly in one direction. The puzzle deepens when you realize that individual atoms don't know about time's arrow. A single molecule bouncing around has no preference for past or future. Its tiny motions are completely reversible. So how does a collection of reversible parts create an irreversible whole? It's like discovering that a symphony, made up of individual notes that could be played in any order, somehow insists on moving from the first measure to the last. This mystery has captivated minds for centuries. The ancient Greeks noticed it, though they described it differently. They spoke of time as a river that carries us forward, never allowing us to step into the same water twice. But they couldn't have known what we know now, that this river's direction might be written into the very fabric of reality itself. Consider your daily experience. You wake up and the day unfolds in a sequence that feels inevitable. Breakfast comes before lunch. Conversations flow from question to answer. Your coffee cools but never spontaneously warms up. Every moment builds on the last, creating a story that moves forward with what feels like inexorable logic. But physics suggests this forward flow isn't guaranteed by the basic rules of the game. The first scientist to really grapple with this was Ludwig Boltzmann, a 19th century Austrian physicist with a magnificent beard and an even more magnificent mind. He realized that time's arrow might emerge from statistics, not the fundamental laws themselves, but from the overwhelming likelihood that certain things happen and others don't. When you drop that glass, there are countless ways for it to shatter, and only one way for it to be whole. The universe, Boltzmann suggested, naturally flows toward the more probable arrangements. But this raises another puzzle. If time's direction comes from probability, why don't we ever see the improbable? Why don't broken glasses occasionally reassemble themselves just by chance? After all, the laws of physics don't forbid it. The answer involves numbers so large they make the age of the universe look like a coffee break. The chances of random motion spontaneously organizing into a perfect glass are so astronomically small that we could wait longer than the universe has existed and never see it happen. There's something almost poetic about this. Time's arrow emerges not from rigid rules, but from the gentle weight of possibility, the quiet insistence of chance guiding the universe toward its most likely futures. It's as if the cosmos has a preference, not enforced by law, but by the simple mathematics of what can be. And yet, the mystery isn't solved. We still don't fully understand why the universe started in such an organized state that it could become disorganized in the first place. Why did time's arrow point the way it does from the very beginning? Why do we live in a universe where entropy increases rather than decreases? These questions take us back to the birth of the cosmos itself, to a moment when time, space, and possibility all began their long dance together. Tonight, as you feel yourself moving forward through these quiet moments toward sleep, you're participating in time's great one-way journey. Your thoughts are settling, your breathing is slowing, your day is gently becoming your past. And in that simple transition from wakefulness to dreams, you're riding time's arrow exactly as the universe intended, flowing with the gentle current that carries all things from what was toward what will be. There's a word that sounds almost musical when you say it slowly: entropy. It rolls off the tongue like a gentle sigh, which is fitting, because entropy is all about things settling down, spreading out, and finding their most relaxed state. And it might just be the key to understanding why time flows in only one direction. Entropy, simply put, is a measure of disorder, but not the kind of disorder that comes from leaving socks on the floor or forgetting to do the dishes. This is cosmic disorder, the universe's natural tendency for energy and matter to spread out, to become more mixed up, more evenly distributed. And here's the beautiful part: entropy almost always increases. Things tend to get more disordered over time, not less. This observation is enshrined in what physicists call the second law of thermodynamics. It states, with elegant simplicity, that in any closed system, entropy tends to increase. Heat flows from hot objects to cold ones, never the other way around. Perfume spreads through a room but never spontaneously gathers back into the bottle. Your coffee cools down but never randomly heats up. These aren't just tendencies. They're expressions of time's deepest pattern. Imagine a brand new deck of cards, perfectly ordered from ace to king in each suit. Now shuffle them. With each shuffle, they become more mixed up, more random. You could shuffle for the rest of your life and never accidentally recreate that perfect order. That's entropy in action, a gentle but relentless drift toward disorder. And here's the crucial part. This drift gives time its direction. But why does entropy increase? The answer lies in simple mathematics, though the implications are anything but simple. There are vastly more ways for things to be disordered than ordered. A neat desk has everything in its proper place. Just one arrangement out of countless possibilities. A messy desk has papers scattered, pens rolling about, books askew, thousands upon thousands of possible arrangements. The universe naturally tends toward the arrangements that are most probable, and disorder is almost always more probable than order. This is where Boltzmann's insight becomes breathtaking. He realized that what we call time's arrow, our sense that time moves from past to future, is really just the universe moving from less probable states to more probable ones. We call the less probable states the past and the more probable states the future. Time's direction isn't something imposed on the universe from outside. It emerges from the mathematical structure of possibility itself. Consider the room you're in right now. The air molecules are bouncing around randomly, but they're distributed fairly evenly throughout the space. It's theoretically possible for all those molecules to suddenly rush to one corner, leaving you gasping in a vacuum while one corner of the room becomes incredibly dense. But the odds of this happening are so small that you could wait longer than the universe has existed and never see it occur. The molecules naturally spread out because there are so many more ways to be spread out than clustered together. This same principle governs everything from the way heat flows to the way stars evolve. When a star burns hydrogen into helium, it's increasing the universe's total entropy. The organized energy locked up in hydrogen nuclei is being converted into the more disorganized form of heat and light. The star can't help but flow forward in time because it's riding entropy's gentle but inexorable current. Even life, beautiful and complex as it is, follows this rule. Yes, living things create incredible order. Your body is an astonishingly organized collection of molecules. But life maintains its order by increasing disorder elsewhere. You eat organized food and excrete less organized waste. You breathe in oxygen and breathe out the more disordered carbon dioxide. Life doesn't violate the second law. It dances with it, creating pockets of order while contributing to the universe's overall drift toward disorder. There's something deeply comforting about this. The arrow of time isn't arbitrary or cruel. It's the natural result of the universe settling into its most comfortable, most probable states. Like water flowing downhill, or a tired person sinking into a soft bed, the cosmos is simply following the path of least resistance, the gentle slope toward maximum entropy. And yet, this creates a puzzle. If entropy always increases, what about the future? Will the universe eventually reach a state of maximum entropy where nothing interesting can happen anymore? Some scientists call this the heat death of the universe, a time when all energy is evenly distributed, all temperatures are the same, and time's arrow finally stops mattering because nothing changes anymore. But that's a story for the very distant future, so far away that our sun will have long since burned out and been forgotten. Tonight, entropy is working in your favor, gently encouraging your busy thoughts to settle, your active mind to spread its energy more evenly, to find its most comfortable, least organized state. As you drift towards sleep, you're following the same universal principle that guides stars and galaxies. The gentle current that gives time its direction and the universe its story. In the beginning, there was nothing. Then, in the smallest fraction of a second imaginable, there was everything. Not scattered and chaotic, but impossibly organized, incredibly hot, and fantastically dense. This is the story of the Big Bang, and it's also the story of how time got its direction. Picture the universe 13.8 billion years ago, compressed into a region smaller than a grain of sand. Everything that would become galaxies, stars, planets, and you were squeezed together in a state of almost perfect order. Perfect order means very low entropy, and low entropy, as we've learned, is what gives time its arrow. The Big Bang didn't just create space and matter. It created the conditions that would make time flow in one direction. But here's what makes this truly extraordinary. Nobody told the universe to start in such an organized state. The laws of physics, by themselves, would be perfectly happy with a universe that began in maximum entropy, completely disordered, with no preferred direction for time. Instead, we got something wildly improbable. A cosmic starting point so organized that it's been increasing in entropy ever since, and will continue to do so for trillions upon trillions of years. Think of it like this. Imagine finding a massive jigsaw puzzle perfectly assembled, sitting on a table in an empty room. You'd naturally wonder who put it together. The Big Bang is like finding the universe's jigsaw puzzle not just assembled, but compressed into a single point, and then exploding outward in a precisely orchestrated fashion. The mystery isn't just how it happened, but why it started so incredibly organized in the first place. In those first moments after the Big Bang, the universe expanded and cooled with breathtaking speed. During a period called cosmic inflation, space itself stretched faster than light could travel, smoothing out irregularities and setting the stage for everything that would follow. It's as if the universe took a deep breath and then exhaled, spreading energy and matter across vast distances while maintaining just enough structure to eventually form stars and galaxies. This expansion created time's arrow on the grandest possible scale. As the universe grew larger and cooler, it naturally became more disordered. Energy that was once concentrated in a tiny, hot point spread out across enormous volumes of space. Temperature differences emerged, allowing heat to flow and work to be done. The very expansion of space itself drives the increase in entropy that gives time its direction. But the Big Bang also explains something else about time. Why we have a past and a future at all. Before the universe began expanding from its initial state, there was no before. Time itself began with the Big Bang. This isn't just a limitation of our knowledge. It's a feature of reality itself. Ask what happened before the Big Bang, and you're asking what's north of the North Pole. The question doesn't have an answer, because it doesn't have a meaning. This creates a beautiful symmetry. The universe's past is the direction toward the Big Bang, toward higher organization and lower entropy. The future is the direction away from the Big Bang, toward lower organization and higher entropy. We live somewhere in between, in an era when the universe is organized enough for stars to shine and life to flourish, but disorganized enough for interesting things to happen. The cosmic microwave background radiation, the afterglow of the Big Bang that still fills the universe today, carries the faint echo of that initial organization. When scientists study this radiation, they're looking at baby pictures of the universe, seeing the tiny variations in the temperature and density that would eventually grow into the cosmic web of galaxies and empty space we see today. It's remarkable that we can observe evidence of the universe's infancy just by pointing sensitive instruments at the sky. And here's something quietly astonishing. The Big Bang doesn't just explain why time has a direction. It also explains why time is woven together with space into what Einstein called space-time. In the beginning, space and time emerged together, stretched together, evolved together. The expansion of the universe isn't just matter moving through space. It's space itself growing larger, carrying time along with it. Some cosmologists wonder whether our Big Bang was the first, or whether the universe goes through cycles of expansion and contraction, each cycle resetting time's arrow. Others speculate about parallel universes or multiple Big Bangs, each creating its own arrow of time. But these remain beautiful mysteries, questions that push against the edges of what we can observe and understand. What we do know is that we live in a universe that started impossibly organized and has been settling into disorder ever since. That process, the gentle, inexorable slide from order to chaos, creates the flow of time that carries your thoughts from moment to moment, your life from birth to death, and the universe from its spectacular beginning toward its peaceful end. Tonight, as you settle into sleep, you're participating in time's cosmic story. Your organized, wakeful consciousness is gradually becoming more relaxed, more diffuse, more settled. You're following the same universal principle that guides the expansion of space itself, the gentle current that began with the Big Bang and continues to carry all things forward through time's one-way journey. Your brain is a time traveler, but it only goes one way. Right now, you can remember what you had for breakfast this morning, but you can't remember what you'll have for breakfast tomorrow. This simple fact that memory points backward while anticipation points forward might be one of the most important clues to understanding why we experience time in only one direction. Memory isn't just storage. It's the foundation of your sense of time's flow. Without it, each moment would feel disconnected from the last, like living in a series of snapshots with no story connecting them. People who suffer from severe amnesia often describe a strange relationship with time, not just difficulty remembering the past, but confusion about whether time is moving at all. Memory doesn't just record time. It creates our experience of time's passage. But here's something fascinating. Your brain doesn't actually store memories the way a computer stores files. Instead, it reconstructs them each time you remember, like rebuilding a house from a set of scattered blueprints. And each reconstruction changes the memory slightly, updating it with new information, current emotions, and present understanding. Your past, in a very real sense, is constantly being rewritten by your present. This process of memory reconstruction reveals something profound about time's direction. You can change your memories of the past, not deliberately, but simply by remembering them. Each time you recall a childhood birthday party or an old conversation, you're not accessing a perfect recording, but creating a new version influenced by everything that's happened since. Your past is surprisingly fluid, shaped by your present in ways that would seem impossible if time were truly linear. Yet you can't remember the future, no matter how hard you try. You can imagine it, plan for it, worry about it, but you can't recall it the way you recall yesterday's sunset. This asymmetry, perfect backward access, zero forward access, mirrors the asymmetry of time itself. It's as if consciousness is built to flow with time's current, not against it. Neuroscientists have discovered that memory formation requires the brain to do something remarkable. It must distinguish between before and after at the cellular level. When neurons form new connections to encode a memory, they're creating a physical record of sequence, a microscopic timestamp that says, this happened after that. The very architecture of memory is built on time's one-way flow. But the brain does something even more extraordinary. It doesn't just record the past. It uses that past to construct a sense of continuous selfhood. You feel like the same person who went to bed last night and woke up this morning because your brain weaves your memories into a continuous narrative. Without that narrative, without the thread of memory connecting each moment to the last, you wouldn't just lose your past. You'd lose your sense of being a coherent self moving through time. This creates a beautiful paradox. Memory, which points backward, is what allows you to move forward. By remembering where you've been, your brain constructs a sense of trajectory, of movement from past toward future. You experience yourself as someone with a history, and therefore as someone capable of having a future. Memory doesn't just record time's passage. It creates your subjective experience of being carried along by time's current. The brain's relationship with time gets even stranger when you consider dreams. During sleep, the usual rules of temporal sequence break down. You might dream of events from different periods of your life jumbled together, or experience impossible sequences where effects precede causes. Yet even in dreams, you rarely experience time flowing backward. Even when logic fails, time's arrow remains remarkably persistent in your consciousness. And then there's that strangest of mental phenomena, déjà vu. For a moment, the present feels like a memory of the past, as if time has somehow looped back on itself. Scientists think déjà vu occurs when memory and perception circuits in the brain briefly misfire, creating the illusion that you're remembering something as it happens. It's a temporary glitch in your brain's time machine, a brief confusion between experiencing and remembering that makes the present feel like an echo of the past. The brain also has an internal clock, a neural network that keeps track of intervals and sequences. This biological timekeeper helps you estimate how long things take, when to expect events, and how to coordinate your actions with the world around you. But unlike the precise atomic clocks that scientists use, your brain's clock is wonderfully, frustratingly subjective. Time flies when you're engaged, crawls when you're bored, and seems to accelerate as you age. This subjectivity suggests something profound. Time's direction might be partly constructed by consciousness itself. The brain doesn't just detect time's flow. It participates in creating your experience of that flow. Memory points backward, attention focuses on the present, and anticipation reaches toward the future, creating a subjective sense of movement through time that mirrors the objective flow of entropy and causation. Perhaps most remarkably, your brain can simulate time travel. When you remember the past or imagine the future, you're using the same neural networks that process the present. Your brain literally creates virtual realities of other times, allowing you to mentally visit yesterday or tomorrow while remaining firmly planted in now. These time-traveling simulations help you learn from the past and plan for the future, but they always originate from and return to the present moment. As you settle into sleep tonight, your brain's time machine will continue its gentle work. It will file away today's experiences, integrate them with older memories, and perhaps offer you dreams that play with time in impossible ways. But even in sleep, even in dreams, you'll continue flowing forward through time's one-way current, carried by the same neural processes that create your sense of self, your connection to the past, and your capacity to greet tomorrow as a conscious, remembering being. Drop a stone into a still pond, and ripples spread outward in perfect circles. The stone's splash causes the ripples, never the other way around. This simple scene illustrates one of the universe's most fundamental rules. Causes precede effects. And this rule, woven into the very fabric of reality, might be the deepest reason why time flows in only one direction. Causality seems so obvious that we rarely question it. You flip a light switch and the bulb illuminates. You speak and sound waves travel outward. You smile and someone smiles back. Cause and effect, action and consequence. Yesterday shaping today, shaping tomorrow. But what would happen if this order could reverse? What if effects could precede their causes? The universe would become a very strange place indeed. Imagine if ripples in a pond could spontaneously converge to launch a stone into the air, or if light bulbs could illuminate before you flip the switch, somehow causing your finger to move. These scenarios don't just feel wrong. They would violate some of the deepest principles of physics and logic. The fact that they never happen suggests that causality isn't just a useful concept. It's a fundamental feature of how reality works. But why does causality flow forward rather than backward? The answer connects to everything we've explored about entropy and time's arrow. In a universe where disorder increases, information tends to spread out and become diluted. When you drop that stone, the organized energy of its impact spreads into the disorganized motion of countless water molecules. This process is easy in one direction, from organized to disorganized, and virtually impossible in reverse. Consider information more broadly. Right now, as you listen to these words, information is flowing from this audio to your ears to your brain. But that information is also spreading in countless other directions. Sound waves bouncing off walls, heat radiating from your device, light scattering in all directions. The universe is constantly taking concentrated information and spreading it around, making it increasingly difficult to trace effects back to their causes as time goes on. This is why forensic science works, but prophecy doesn't. A detective can examine a crime scene and work backward to determine what happened, because the past leaves traces in the present. Blood spatter patterns, fingerprints, DNA evidence. These are all effects that point back to their causes, but nobody can examine the present and determine with certainty what will happen in the future, because future effects haven't left their traces yet. The speed of light plays a crucial role in maintaining causality's direction. Nothing can travel faster than light, which means that cause and effect are always separated by a minimum amount of time. If you push a button here and a light turns on there, the signal traveling between them, whether electrical, optical, or mechanical, cannot exceed light speed. This creates what physicists call the light cone, a mathematical description of which events can possibly influence which other events. Within your past light cone lie all the events that could have influenced your present moment. Within your future light cone lie all the events your present moment could possibly influence. This structure ensures that causes always precede effects, that information always flows from past to future, never the other way around. It's as if the universe has a built-in traffic control system, keeping causality flowing in one direction to prevent temporal paradoxes. But what about quantum mechanics, where particles seem to defy common sense? Even in the quantum world, causality's arrow remains intact. When quantum particles become entangled, they seem to influence each other instantaneously across vast distances. But this spooky action at a distance, as Einstein called it, can't actually transmit information faster than light. The correlations between entangled particles are real, but they can't be used to send messages from effect to cause or to violate causality's forward flow. There's something deeply satisfying about causality's reliability. It means the universe has a logical structure, that actions have consequences, that effort can lead to results. Without causality's arrow, there would be no learning, no growth, no meaningful choice. The fact that today's decisions shape tomorrow's outcomes is what makes life feel purposeful rather than random. Causality also creates the possibility of understanding. Science works because we can trace effects back to causes, identifying the mechanisms that connect events across space and time. Every scientific law, from gravity to evolution, describes causal relationships, how certain conditions reliably lead to certain outcomes. Without causality's forward flow, the universe would be incomprehensible, a chaotic jumble of unconnected events. Yet causality isn't always simple. In complex systems, causes and effects can form intricate webs with feedback loops and emergent properties that make prediction difficult. The butterfly effect. The idea that a butterfly's wings might eventually influence weather patterns on the other side of the world illustrates how small causes can have large effects through cascading chains of causation. Even in a perfectly causal universe, the future can remain beautifully unpredictable. And then there are questions that push at the edges of causality itself. What caused the Big Bang? What causes the laws of physics to be what they are? These questions may be unanswerable, not because we lack knowledge, but because they reach beyond the domain where causality applies. Perhaps causality, like time itself, emerged with the universe rather than existing as some eternal truth. Free will presents another puzzle. If every event is caused by previous events, are your choices really choices, or just the inevitable result of a causal chain stretching back to the Big Bang? This is one of philosophy's oldest questions, and it remains beautifully unresolved. Perhaps consciousness creates a kind of top-down causation, where your thoughts and decisions become genuine causes rather than mere effects. As you drift towards sleep, causality continues its quiet work. The relaxation of your muscles causes changes in your blood flow. Your slowing thoughts cause shifts in your brainwaves. Each cause leads to its effect in perfect sequence, following the same universal principle that governs everything from falling leaves to orbiting planets. You're part of causality's great chain, both shaped by the past and shaping the future, carried forward by time's current toward whatever tomorrow will bring. In the strange realm of quantum mechanics, where particles can be in multiple places at once and reality seems to shift based on observation, time becomes wonderfully, bewilderingly complicated. Here, in the smallest scales of existence, some of our most basic assumptions about time's direction begin to wobble like a compass near a magnet. At the quantum level, many processes are fundamentally reversible. An electron can absorb a photon and jump to a higher energy level, or it can emit a photon and drop to a lower level. Run the equations backward, and they work just as well forward. Watch a film of a single electron bouncing around, and you'd have trouble telling whether it was running forward or in reverse. The microscopic world seems oddly indifferent to time's arrow. This creates a fascinating puzzle. If individual quantum processes don't care about time's direction, how does the macroscopic world, built from countless quantum particles, develop such a strong preference for forward? It's like discovering that every individual musician in an orchestra is playing random notes, yet somehow the entire ensemble produces a symphony with a clear beginning, middle, and end. The answer lies in what physicists call decoherence. When quantum systems interact with their environment, which is almost always, they lose their quantum weirdness and begin behaving more classically. This interaction typically increases entropy, and entropy, as we've seen, gives time its arrow. So while individual quantum events might be reversible, their collective effect pushes the universe toward greater disorder and forward through time. But quantum mechanics offers some truly mind-bending possibilities for time. Quantum tunneling allows particles to pass through barriers that should, classically, be impossible to cross. In a sense, the particle borrows energy from the future, uses it to cross the barrier, and then pays it back, all within the constraints of Heisenberg's uncertainty principle. It's as if time itself becomes slightly flexible at quantum scales, allowing brief loans against future possibility. Even stranger is the quantum Zeno effect, where frequent observation of a quantum system can freeze its evolution. It's named after the ancient Greek philosopher Zeno, who argued that motion was impossible because any moving object must pass through infinite intermediate positions. In the quantum version, if you watch a radioactive nucleus carefully enough, you can actually prevent it from decaying. Observation doesn't just reveal quantum reality, it shapes it. And sometimes that shaping can slow or even stop the passage of time at quantum scales. Then there's quantum entanglement, Einstein's spooky action at a distance. When particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This seems to violate everything we know about causality and time's arrow. How can an effect occur faster than light could travel between cause and effect? The resolution is subtle. While the correlations between entangled particles are instantaneous, no information actually travels faster than light. It's like having two perfectly synchronized coins that always land on opposite sides. Miraculous correlation, but no communication. Some interpretations of quantum mechanics suggest even more radical possibilities for time. In the many worlds interpretation, every quantum measurement splits the universe into multiple branches, each representing a different outcome. From this perspective, time doesn't just flow forward. It branches like a river delta, with countless parallel timelines spreading out from every quantum event. You might be flowing through one particular branch of time, while other versions of yourself explore different branches entirely. The delayed choice quantum eraser experiment pushes these ideas to their limits. In this setup, the quantum nature of a particle's past seems to depend on measurements made in its future. It's as if the future can reach back and influence what really happened in the past. Not changing history, but determining which version of a history actually occurred. Time, at quantum scales, becomes less like a river and more like a vast, interconnected web, where past and future are mysteriously entangled. Quantum field theory, which describes the fundamental forces and particles, introduces another wrinkle: virtual particles. These ephemeral entities pop into existence from the quantum vacuum, briefly interact, and then annihilate each other, all within time frames so short that they respect Heisenberg's uncertainty principle. Some virtual particles can travel backward in time, though this is interpreted as antimatter particles traveling forward in time. Even in the quantum world, time's overall direction remains intact. The measurement problem in quantum mechanics raises profound questions about the role of consciousness in physics. Before measurement, quantum systems exist in superposition, all possible states simultaneously, but measurement collapses this superposition into a single outcome. What counts as measurement? Does consciousness play a special role? Some interpretations suggest that conscious observation is what causes quantum systems to choose one history over another, making consciousness an active participant in the flow of time itself. Quantum computers exploit these temporal mysteries in fascinating ways. They use quantum superposition to perform calculations on multiple possible answers simultaneously, then use quantum interference to amplify the correct answer. In a sense, they explore many possible computational timelines in parallel before converging on a single result. They don't violate time's arrow, but they dance with it in ways that classical computers cannot. Perhaps most remarkably, some theories suggest that time itself might be quantized, made up of discrete, indivisible units like frames in a movie. These hypothetical units, called Planck time units, would be incredibly small, about 10⁻43 seconds. If time really is quantized, then beneath the smooth flow we experience lies a digital reality, with existence stuttering forward in quantum steps too small to perceive. As you settle into sleep, quantum processes continue their mysterious dance throughout your body. Electrons tunnel through biological barriers, enabling the chemistry of life. Quantum effects in your brain's microtubules might even play a role in consciousness itself, though this remains beautifully speculative. You're not separate from the quantum world. You're built from it, sustained by it, carried forward through time by the same quantum currents that shape atoms and stars. The quantum realm reminds us that time's mysteries run deeper than we might imagine. Even as we experience time flowing steadily forward, the foundation of reality pulses with possibilities, superpositions, and correlations that transcend our everyday intuitions about past, present, and future. Time's arrow remains intact, but at quantum scales, it flies through a landscape far stranger and more wonderful than we ever suspected. What time is it right now? The moment you answer that question, now, has already become then. The present moment, this instant you're experiencing as you hear these words, is the most immediate thing you know, yet it might be the most mysterious aspect of time. Some physicists argue that now doesn't exist at all, that it's an illusion created by consciousness flowing through a universe where past, present, and future are equally real. This idea, called the block universe theory, suggests that all moments in time exist simultaneously, like frames in a movie reel. From this perspective, yesterday, today, and tomorrow are all equally present. We just experience them one at a time, like reading a book page by page, when the entire story already exists. Einstein himself leaned toward this view, once comforting a friend by saying that for physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. But if that's true, what creates our experience of moving through time? Why does consciousness seem to flow from moment to moment rather than experiencing all times at once? The answer might lie in the nature of memory and awareness themselves. Your sense of now isn't actually a single instant, but a brief window of experience, typically lasting a few seconds, during which your brain integrates sensory information, processes thoughts, and maintains consciousness. Neuroscientists call this the specious present, the duration of your immediate conscious experience. It's specious because it's not actually instantaneous but feels like it is. When you listen to music, you don't experience individual notes as isolated points in time, but as melodies flowing through this window of awareness. Your brain takes these sequential events and weaves them into the seamless experience of now. This window of awareness creates what feels like motion through time. As new information enters your consciousness and old information fades into memory, you experience the sensation of the present moment advancing. It's like sitting in a train and watching the landscape pass by. The train, your consciousness, stays put, while the scenery, moments in time, flows past the window. Except in this case, you might be the one moving through a stationary landscape of moments. The brain accomplishes this remarkable feat through a complex orchestration of neural activity. Different brain regions process information at different speeds. Visual processing, auditory processing, and motor control all operate on their own timescales. Yet somehow, your brain synchronizes all this activity to create a unified experience at the present moment. It's like conducting an orchestra where every musician is playing at slightly different tempos, yet the result is perfectly coordinated music. But here's where it gets truly strange. Your brain actually predicts the present. Because neural processing takes time, by the time your brain has processed sensory information, the world has already moved on. To compensate, your brain constantly makes predictions about what's happening now based on what it sensed a moment ago. Your experience of the present is actually your brain's best guess about reality, projected slightly into the future to account for processing delays. This predictive nature of consciousness creates fascinating distortions. Have you ever noticed that when you move your eyes quickly from one point to another, you don't see the blurry motion in between? Your brain edits out that motion and creates the illusion of seamless vision. Or consider the color-fi phenomenon, where flashing lights of different colors create the illusion of a colored object moving between them. Your brain constructs a story of motion and color change that never actually occurred, filling in details to create a coherent narrative of the present moment. Some philosophers argue that this constructed nature of now reveals something profound about time itself. If the present moment is assembled by consciousness from memories of the immediate past and predictions of the immediate future, then perhaps the flow of time isn't something we experience, but something we create. We might not be passive observers riding time's current, but active participants in constructing time's flow through the act of being conscious. Different states of consciousness offer glimpses into time's malleable nature. During meditation, practitioners often report that the sense of temporal flow changes or even stops entirely. In flow states, moments of intense focus and engagement, hours can pass unnoticed. Under anesthesia, consciousness disappears, and with it the sense of time's passage. These experiences suggest that our normal perception of flowing time is intimately connected to specific patterns of neural activity. Dreams present another puzzle for the present moment. In dreams, you experience a sense of now, but it's divorced from external time. Dream events can feel like they last for hours when they occur in minutes of sleep. Time dilates, contracts, and sometimes seems to flow backward. Yet even in dreams, consciousness maintains some sense of present moment awareness, suggesting that the experience of now is more fundamental to awareness than its connection to external time. The physics of relativity adds another layer to the mystery of now. Einstein showed that simultaneity is relative. Events that appear to happen at the same time, to one observer might appear sequential, to another observer moving at a different speed. This means there's no universal now that applies everywhere in the universe. Your present moment is different from the present moment of someone moving relative to you, and both are equally valid. The universe doesn't have a single shared now. Yet despite all these complications, the experience of the present moment remains vivid and immediate. You feel yourself existing right now, thinking these thoughts, breathing this breath. That experience might be constructed, predicted, and relative, but it's also undeniably real. Perhaps the illusion of now is the most important illusion of all, the one that makes consciousness possible, that creates the stage on which awareness can unfold. As you drift towards sleep, your sense of the present moment will gradually fade. The sharp focus of wakeful consciousness will soften into the looser, more fluid awareness of dreams. Time's arrow will continue carrying you forward, but your experience of traveling along it will change, becoming less defined, more mysterious. And in that transition from the clear now of wakefulness to the strange temporality of sleep, you'll glimpse something profound about the relationship between consciousness and time, how they dance together to create the experience of being here, now, in this moment that is always slipping away into the next. In a hidden laboratory, scientists regularly witness time flowing backward, not in some science fiction story, but in real experiments happening right now. These aren't violations of physics, but revelations of just how subtle time's relationship with reality truly is. While the large-scale universe flows steadily forward, there are corners of physics where time can, quite literally, change direction. The most dramatic example occurs with antimatter. When an antiparticle moves forward through time, the mathematics of physics describes it identically to its corresponding particle moving backward through time. An electron moving forward and a positron, an anti-electron, moving backward are, in the language of physics, the same thing viewed from different temporal perspectives. It's as if the universe has a kind of temporal symmetry, where every forward process has a backward counterpart hiding in the world of antimatter. This isn't just theoretical elegance. In particle accelerators around the world, scientists create antimatter routinely, and these antiparticles behave exactly as if they were normal particles running time's arrow in reverse. When they meet their matter counterparts, they annihilate in perfect symmetry, converting mass into energy in a process that treats forward and backward time with equal respect. At the quantum level, many processes are fundamentally reversible. An atom can absorb a photon and emit it later in a process called stimulated emission, the principle behind lasers. Run the equations describing this process backward, and they remain perfectly valid. The atom could just as easily have been in the excited state first, emitted the photon, and ended up in the ground state. Time's direction emerges only when you consider the larger context, the source of the photon, the ultimate destination of the energy. Even more remarkable are time reversal experiments with individual quantum particles. Scientists have learned to create what they call time-reversed quantum states, configurations that evolve backward through their previous history. Imagine filming a quantum system evolving forward. then carefully preparing an identical system to evolve exactly backward through the same sequence of states. The quantum world permits this temporal choreography with startling precision. Nuclear magnetic resonance experiments demonstrate this beautifully. Scientists can apply carefully timed magnetic pulses to make atomic nuclei forget their recent history and return to previous states. It's like convincing a collection of atomic compasses to retrace their steps, unwinding their magnetic evolution until they return to where they started. Time, at this scale, becomes something that can be rewound like a recording. But perhaps the most mind-bending time reversal occurs in quantum mechanics itself. Some interpretations suggest that quantum measurements don't just reveal the present state of a particle, but can influence its entire history. In these retrocausal interpretations, the future can reach back and help determine what happened in the past. It's not that the past changes, but that the past was always uncertain until the future measurement gave it definition. Superconductivity offers another window into time's flexibility. In superconducting materials, electrons form pairs that can flow without resistance, creating electrical currents that, in principle, could flow forever. These persistent currents exist in a kind of temporal loop, neither advancing nor retreating, but maintaining perfect stasis. It's as if time becomes crystallized, frozen into persistent patterns that neither grow nor decay. The mathematics of physics reveals an even deeper symmetry. Most fundamental equations remain valid if you simultaneously reverse time, flip all charges, turn matter into antimatter, and mirror space, flip left to right. This CPT symmetry, charge, parity, time, suggests that the universe has a kind of grand reversibility built into its foundation. For every process moving forward through time, there exists, in principle, a corresponding process moving backward. Yet these time reverse processes don't accumulate into macroscopic time reversal. A superconducting current flowing forever doesn't make the superconductor younger. Antimatter behaving like time reverse matter doesn't cause the laboratory to age backward. Time's arrow at large scales emerges from the collective behavior of countless microscopic processes, each individually reversible, but collectively irreversible. Some scientists speculate about more dramatic forms of time reversal. Theoretical physics permits the existence of closed time-like curves, paths through space-time that loop back to their own beginning. These would allow genuine time travel into the past, though they would require exotic matter with properties we've never observed. The universe seems to protect causality through what physicists call the chronology protection conjecture, natural laws that prevent paradoxes by forbidding actual time travel. Quantum computers exploit time's subtle reversibility in fascinating ways. Quantum algorithms often involve running calculations forward and then backward, using interference between forward and reverse processes to amplify correct answers and cancel out wrong ones. These machines don't violate time's arrow, but they dance with it in ways that classical computers cannot, exploring multiple computational timelines before converging on a single result. The second law of thermodynamics, which drives time's arrow through increasing entropy, has fascinating exceptions at small scales. For very small systems observed for very short times, entropy can spontaneously decrease. Molecular motors in living cells sometimes step backward, temporarily violating the usual relationship between energy and motion. These fluctuations don't reverse time's arrow, but reveal its statistical nature. Even the most fundamental laws of physics have microscopic exceptions. Perhaps most remarkably, some theories suggest that information itself might be reversible. Quantum information can be copied, entangled, and transmitted in ways that preserve perfect reversibility. If consciousness is somehow based on quantum information processing, then perhaps awareness itself participates in time's reversibility, experiencing forward flow while remaining fundamentally atemporal at its deepest level. As you settle into sleep, your body hosts countless examples of time's subtle reversibility. Chemical reactions proceed forward and backward in delicate balance. Neural processes that built today's memories could, in principle, be reversed to erase them. Yet these microscopic reversibilities combine to create the irreversible flow of your life, from birth toward death, from wakefulness toward sleep, from today toward tomorrow. You exist in the beautiful tension between time's fundamental reversibility and its emergent direction, carried forward by the same physical laws that permit, but rarely produce, journeys into the past. Every heartbeat carries you forward through time. Every breath draws you deeper into the future. Right now, as you listen to these words, millions of biological processes are unfolding in perfect temporal coordination, each one a tiny clock helping to weave your life into time's one-way tapestry. Living things don't just exist in time. They are time, embodied in flesh and blood, and the endless dance of molecules that transform past into future. Your circadian rhythm is perhaps the most obvious example of biology's relationship with time. Deep in your brain, a cluster of neurons called the suprachiasmatic nucleus acts as your master biological clock, synchronized to Earth's rotation by the daily cycle of light and darkness. This internal timekeeper orchestrates everything from your sleep-wake cycle to your body temperature, hormone levels, and even the activity of genes throughout your cells. But the circadian clock is just the beginning. Your body contains a hierarchy of biological timers operating on scales from microseconds to years. Your neurons fire in precise temporal patterns, creating the rhythms of thought and consciousness. Your heart beats with mechanical regularity, while your breathing follows its own gentle oscillation. Even individual cells have their own clocks, timing everything from protein synthesis to DNA repair to the controlled death that maintains healthy tissues. These biological clocks don't just measure time. They create temporal order. Without them, the intricate chemistry of life would collapse into chaos. Enzymes wouldn't know when to activate. Hormones wouldn't know when to release. Cells wouldn't know when to divide. Time isn't just the medium in which life unfolds. It's one of life's essential organizing principles, as fundamental as energy or information. Yet biological time is wonderfully flexible compared to physical time. Your perception of duration changes with age, attention, and emotion. Children experience time more slowly than adults, perhaps because their brains are processing more new information per unit time. When you're engaged in absorbing activities, hours can pass like minutes. When you're bored or anxious, minutes can stretch like hours. Your biological experience of time's passage varies with your internal state, not just the external clock. This subjectivity reveals something profound about living in time's current. Unlike a rock or a planet, which simply endure through time's passage, living things actively participate in creating their temporal experience. Your brain doesn't just detect time's flow. It constructs your sense of duration, sequence, and rhythm from the complex interplay of memory, attention, and prediction. You're not a passive passenger on time's river, but an active navigator, steering your consciousness through the flow of moments. Sleep offers a fascinating window into biology's relationship with time. During certain stages of sleep, your sense of time's passage virtually disappears. Hours can pass unnoticed, with consciousness emerging only during brief interludes of dreaming. Yet even in sleep, biological time continues its work. Your body temperature cycles, your immune system strengthens, your brain consolidates memories. Time's arrow keeps carrying you forward even when you're not aware of the journey. Dreams create their own temporal landscape, one often disconnected from external time. In dreams, you might experience events from different periods of your life jumbled together, or live through sequences that would take hours in minutes of sleep. Dream time follows psychological rather than physical logic, revealing how consciousness can construct its own temporal reality, independent of clocks and calendars. The aging process embodies time's arrow in the most personal way possible. Your cells accumulate damage over time, telomeres shorten with each division, and biological systems gradually lose their precision. Yet aging isn't simply decay. It's also development, the accumulation of experience and wisdom that only comes from moving through time. You're not just wearing out as you age, you're becoming something that couldn't exist without a history. Biological evolution operates on an even grander temporal scale, with time's arrow carved into the very structure of life itself. The genetic code carries information accumulated over billions of years, each generation adding to or modifying this vast library of biological knowledge. Your DNA is a historical document, recording the passage of countless generations from the first living cells to you. Evolution doesn't just happen in time. It is time made visible in the changing forms of life. Plants and animals have evolved exquisite sensitivity to temporal patterns. Migrating birds navigate by seasonal changes, flowers bloom in response to day length, and many species coordinate their reproduction with annual cycles. These creatures aren't just responding to time, they're reading the temporal signatures written into light, temperature, and seasonal change, using time itself as a source of information about their environment. Even at the molecular level, life shows remarkable temporal sophistication. Biological molecules often have built-in timers, proteins that fold and unfold on precise schedules, enzymes that activate and deactivate in coordinated cascades, genes that turn on and off in temporal patterns that span hours, days, or years. Your body is a vast orchestra of molecular clocks, each keeping its own time while contributing to the symphony of your existence. The social dimension of biological time adds another layer of complexity. Humans are intensely social creatures, and we coordinate our biological rhythms with others through shared schedules, rituals, and cultural practices. Families eat together, communities celebrate seasonal festivals, and entire societies organize around collective temporal frameworks. Your individual biological time is embedded in social time, which is itself embedded in the cosmic time of planetary rotation and solar cycles. As you drift towards sleep, your biological clocks are already preparing for tomorrow. Your immune system is ramping up its nighttime activities. Your brain is beginning the process of memory consolidation, and your circadian rhythm is orchestrating the complex physiological changes that will carry you through the night and wake you refreshed in the morning. You're not separate from time's flow. You are time's flow, embodied in the countless biological processes that transform each moment into the next, carrying your life forward on the same cosmic current that moves stars and galaxies through their ancient dance. After wandering through entropy and consciousness, causality and quantum mechanics, we arrive at perhaps the most honest place in our journey, the admission that time's deepest nature remains beautifully, stubbornly mysterious. Despite centuries of scientific investigation and philosophical reflection, fundamental questions about time's direction persist at the very edges of human understanding, inviting us into wonder rather than certainty. Consider this puzzle. If the laws of physics are largely reversible, and if the universe began in a highly organized state, why don't we ever observe large-scale time reversal? Why don't we see broken cups spontaneously reassembling, or aging creatures suddenly growing younger, or heat flowing from cold objects to hot ones? The statistical answer, that such events are phenomenally unlikely, feels incomplete somehow, like explaining a symphony by describing the mathematics of sound waves. The mystery deepens when we consider consciousness itself, your subjective experience of time, the feeling of moving from past through present toward future, has no clear counterpart in physics. The equations that describe reality don't include terms for now or the flow of time. They describe correlations between different temporal coordinates, but not the feeling of being carried along by time's current. Your most immediate experience of time might be the very thing science finds hardest to explain. This creates what philosophers call the hard problem of time consciousness. We can describe the neural mechanisms that create your sense of temporal flow, map the brain regions involved in temporal processing, and measure the psychological factors that affect time perception. But none of this explains why you experience a flowing present moment, rather than simply processing temporal information without the subjective sense of movement through time. Some scientists suggest that consciousness doesn't just experience time, but participates in creating it. In quantum mechanics, observation seems to play a special role in determining reality. Perhaps consciousness, through the act of observation and memory formation, helps to crystallize the flow of time from the quantum possibilities that surround each moment. This would make you not just a passive observer of time's passage, but an active participant in its creation. The relationship between time and information presents another profound mystery. Information seems to flow from past to future, accumulating in complex patterns that we call memory, knowledge, and history. But what is information really? Is it a fundamental feature of reality, like energy or matter? Or is it something that emerges from more basic processes? The answers to these questions might hold keys to understanding time's direction. Black holes offer perhaps the most extreme challenge to our understanding of time. At the event horizon, time appears to stop from an outside observer's perspective. Inside a black hole, the roles of space and time seem to reverse, with the singularity lying not in space, but in your inevitable future. What happens to time's arrow in such extreme conditions? Does it reverse, disappear, or transform into something unrecognizable? The possibility of multiple universes adds another layer of mystery. If the many worlds interpretation of quantum mechanics is correct, then every quantum event splits reality into parallel branches, each with its own timeline. From this perspective, time doesn't just flow forward, it branches endlessly, creating countless parallel streams of history, You might be riding just one current in an infinite river of possible times. Even more speculatively, some theories suggest that time itself might be emergent rather than fundamental. Just as temperature emerges from the average motion of countless molecules, time's flow might emerge from more basic, timeless processes. In this view, time's arrow wouldn't be written into the foundation of reality, but would arise from the statistical behavior of underlying timeless entities. The direction of time might be like the direction of a river, an emergent property that appears only when you zoom out to see the larger pattern. The digital physics hypothesis proposes that reality itself might be computational, with the universe operating like a vast computer processing information according to simple rules. If this is true, then time's arrow might simply be the direction in which this cosmic computation proceeds, from input to output, from simple initial conditions to complex emergent patterns. You might be both a process running on this universal computer and a pattern of information flowing through its computational time. String theory and other approaches to quantum gravity suggest that space and time themselves might not be fundamental, but emergent properties of something deeper and stranger. In these theories, the basic constituents of reality might be entities that exist outside conventional space-time altogether. Time's arrow might emerge only at scales large enough for space-time itself to manifest, leaving the deepest layer of reality completely atemporal. Perhaps most mysteriously, the arrow of time might be connected to consciousness in ways we don't yet understand. The fact that conscious observers always experience time flowing forward, never backward, might not be a coincidence. Some theories suggest that consciousness and time's arrow are intimately related, that the direction of time emerges from the structure of information processing that creates awareness itself. These mysteries aren't failures of understanding, but invitations to deeper wonder. They remind us that despite all our scientific progress, reality retains profound secrets. The fact that you experience this moment flowing into the next, that you remember yesterday and anticipate tomorrow, that you exist as a conscious being carried forward by time's current. These are not just facts to be explained, but miracles to be contemplated. As you settle into sleep, you're entering one of time's most mysterious territories. Dreams unfold in their own temporal landscape. Memories reorganize themselves in ways we barely understand, and consciousness itself transforms into something stranger and more fluid. The deep mystery of time's direction continues to enfold you, carrying you forward through the night toward whatever revelations tomorrow might bring. And so, dear listener, we arrive at the end of our gentle journey through time's one-way path, though perhaps end isn't quite the right word. After all, we've learned that time keeps flowing forward, carrying this moment into the next and the next, in an endless procession that began with the universe itself. We've wandered from broken glasses to the Big Bang, from entropy's quiet insistence to memory's strange magic. We've seen that time's arrow isn't cruel or arbitrary, but emerges from the beautiful mathematics of possibility. The universe's patient drift from order toward its most comfortable, most probable states. And through it all, we've discovered that this one-way flow isn't a prison, but a gift. The very thing that makes change possible, that allows stories to unfold and dreams to bloom. Right now, in this gentle moment, you're riding time's current exactly as the cosmos intended. Your day is becoming your past. Your wakefulness is settling into rest. Your thoughts are following entropy's peaceful path toward sleep. You're part of time's great story, flowing forward with everything else in the universe, from distant galaxies to the quiet rhythm of your breath. If this wandering through time's mysteries brought you any peace, if the wonder of it all helped settle your mind, we'd be honored if you join us again for more journeys through science's beautiful puzzles. Thanks for spending your time here with us at Sleep Science, where every question leads gently toward rest and every answer whispers you softly toward dreams. Sleep well, and may time carry you peacefully through the night.